Hey, what's going on, guys? Welcome back to another math video tutorial. In this video, I'm going to be showing you how the parent function of a square root looks like when it's graphed. And we're also going to compare the square root parent function with various transformation rules. So this is going to be very useful when you are asked to determine the domain and range of a square root parent function or a transformation of the square root parent function at a later time. But today we're just going to be comparing the square root parent function with its transformations. So this is our parent function for a square root, and you'll notice that it starts at the origin and it curves to the right. So this is what we're going to be looking at. We're going to be manipulating the parent function, which is y is equal to the square root of x, or sometimes you'll see f of x is equal to the square root of x, and we're going to be changing or adding or taking away elements to the parent function to see how it changes. So the first type of transformation or change that we're going to be looking at is a horizontal translation, which basically means shifting your graph from left or right. And so when we're talking about f of x notation, this is the rule, f of x minus h, which basically means that whatever number you introduce inside of the square root or the radical, it's going to cause a change or a shift of the graph from left to right. So here are two examples. In this example, you'll notice that we have g of x is equal to x to the square root of x minus 2. So in this case, our h, if we're talking about f of x notation, our h is going to be 2. We're taking at the actual value. And so what that's going to do, it's going to cause the square root function to move 2 units to the right. The other example that we have is g of x is equal to the square root of x plus 3. So this one, a lot of students get confused because they think that it makes a shift to the right because of the plus 3, but it's not. You want to take the opposite because, again, we're looking at the notation, we're looking at the actual h. So in this case, our true h would be negative 3. Therefore, it's going to be moving 3 units to the left. But if that, like I said, if that confuses you, just take the opposite. Here, the square root of x minus 2, take the opposite of minus 2, it's going to be plus 2, so it's going to go 2 units to the right. The opposite of plus 3 is going to be negative 3, so it's going to go 3 units to the left. And I have a graph here. I'm going to try to zoom in so I can kind of show you what that shift looks like. So again, we have our parent function, which is our original function. It starts at the origin. And then we had our first transformation, the square root of, or g of x is equal to the square root of x minus 2. Notice it moved to the right, 2 units to the right. It did the opposite of what it looks like it'll do. And then for the blue one, you'll notice that it moved 3 units to the left from the original function. But when you graph it, or when you write it, it looks the square root of x plus 3. Okay, next one. Now, for the next type of transformation, we have what we call a vertical translation, which means that the graph is going to shift up or down. Now, this one is pretty straightforward. The function notation is f of x plus k, so we're going to be adding or subtracting something to the original function, and it's going to be on the outside. And this, we take it for what it is. So, for example, we have g of x is equal to the square root of x plus 7. Well, we noticed that we added a 7 to the original function of the square root of x, which means that the graph is going to shift 7 units up. In contrast, we have g of x is equal to the square root of x minus 1. Notice we subtracted a 1 from the original function, so this is going to cause a shift down from the original function. And so we're going to go ahead and look at the graph as examples so we can kind of see that change. Try not to focus too much on the scaling. The scaling kind of looks a little bit funky, but we're looking at the original function as reference, right? F of x is equal to the square root of x. It starts at the origin. When we added 7, it caused a shift 7 units up. When we took away 1, or we subtracted 1 from the original function, it shifted the graph down. All right. Now, the next type of transformation that we're going to be looking at is called a reflection. And there's two types of reflection. One where it flips over the x-axis, and then another one where it flips over the y-axis. So here we have our function notation. The negative is going to be on the inside of the function. If we're talking about a horizontal reflection or a reflection over the y-axis, and the negative is going to be outside of the original parent or the parent function if we're talking about a reflection over the x-axis or a vertical reflection. So let's look at the examples. Again, the negative is inside of the function, so we're going to have a reflection in the y-axis or a horizontal reflection. And then the other example, the negative is outside of the radical, so we're going to have a reflection on the x-axis or a vertical reflection. So let's look at our examples here. Always referencing our parent function, right? If we have a negative inside of the radical, inside of our function, that's going to cause a reflection over the y-axis, which is a horizontal reflection. And then in the other example, we have the negative outside of the function or outside of the radical, which is going to cause a reflection over the x-axis, which is a vertical reflection. This is reflecting over the x-axis. All right, moving on. Okay, the next type of transformation that we're going to be looking at is called a horizontal stretch or shrink, where the graph stretches away from or shrinks towards the y-axis. Okay, so this is another tricky type of transformation because when we're talking about the factor, we're going to take the reciprocal of what it is, or the opposite. So this is the function notation, f of a times x, and it's a transformation that we're doing inside of our function. So in this first example, we have g of x is equal to the square root of 3 times x. And here we have a 3, but that's not going to be our true a or our true factor, because for horizontal shrinks and stretches, we have to take the reciprocal. So in this case, if it's 3, we're going to take the reciprocal of 3, which is going to be 1 over 3. And since there's a rule where if our true factor is between 0 and 1, then we're going to have a horizontal shrink. And if our true factor is greater than 1, then we're going to have a horizontal stretch. So going back to 3, our reciprocal of 3 is 1 over 3. So our true a or our true factor is 1 over 3. So that's going to be a horizontal shrink. And then for the second example, g of x is equal to the square root of 1/2 x. Because it's inside, we need to take the reciprocal to get our true a, which is going to be 2 over 1. Divide 2 by 1, that's going to give us a true factor of 2. So we're going to have a horizontal stretch. So let's look at our graphs and see how that transformation happens. So looking at we always want to use our parent function as our reference point. So here we have our parent function of f of x is equal to the square root of x, right? And then we are comparing our parent function with our first example where we had a 3, but our true factor was 1 over 3, so we said it was a horizontal shrink. So notice how it's a horizontal shrink because it's shrinking towards the y-axis. So we're seeing that it's a horizontal shrink. If we're comparing from our original parent function, we're seeing that it's moving away from the parent function, so it's shrinking. And then in the second example, we have g of x is equal to the square root of 1/2 times x. Our true a is going to be 2, which means it's a stretch. And so in this example, this function is stretching away from the parent function. It's stretching away from the y-axis, right? So we're calling that as a horizontal stretch. All right. For our final type of transformation, we have what's called a vertical stretch or shrink, where your graph is stretching away from or shrinking towards the x-axis. So the x-axis, that's our reference. So with this one, this is an outside transformation. So we're introducing an element to our original function outside. So going to our example, notice here we have 4 times the square root of x. And the nice thing about this one is you don't have to take the reciprocal. You just take that value for what it is, as that's your true a. So since this is a 4, using the same rule we used previously, 4 is greater than 1. So we're going to have a vertical stretch. And in the second example, it's 1 over 5. Since 1 over 5 is between 0 and 1, we're going to have a vertical shrink. So again, stretch by a factor of 4, and then we have a shrink by a factor of 1 over 5. And in this case, our reference is the x-axis. So let's look at our example here, our graph. So we have our parent function, which is f of x is equal to the square root of x, right? We're using our x-axis as our reference. So notice, from our original function, if we're looking at the first example, 4 times the square root of x, we said it was a vertical stretch. It's stretching away. It's stretching away from the original function. So it's stretching away from the x-axis. In the second example, we have g of x is equal to 1 over 5 times the square root of x. Well, in this case, notice that our transformation is shrinking because it's moving towards the x-axis. So when it's moving away from the x-axis, we have a stretch. When it's moving towards the x-axis, we're going to have a shrink. So that's kind of a quick crash course on the different types of transformations that we can see when it comes to graphing a square root function. And sometimes you're going to see that you can even stack some of these transformations. So, but that's for another video. So I hope that you found this video tutorial helpful. Stay tuned for more math tutorial videos.